Welcome back to the course on symmetry, stereochemistry and applications. In the previous lecture, we have discussed about the various conformational aspects related to cyclohexane and substituted cyclohexane molecules. So now we would like to move to the next part of this course, which is to talk about the aspects of isomerism and how to represent different isomers using projection formula and their significance. We all know that isomers are compounds that have the same numbers and kinds of atoms but different in the way the atoms are arranged. So let us try to see what are different types of isomers that are known. Isomers are specifically divided into two parts: stereoisomers and constitutional isomers. Stereoisomers are further subdivided into two parts: enantiomers and diastereomers, and then the diastereomers are again further classified into four sections, which are geometric isomers or cis and trans isomers, conformational isomers, mesocompounds, and the epimers. So we will slowly learn about all these different classifications of isomers through these lectures. So when we try to first understand what are the constitutional isomers, we should know that constitutional isomers may have different carbon skeleton. That means you may have the molecular formula same but may have a different carbon skeleton, as is shown here in this particular example, where you can have butane in a chain or linear form, or the butane having a branch using a methyl group and forming as isobutane. So that is a constitutional isomer. A different functional group may give rise to isomerism. For example, we all know in case of ethanol and dimethyl ether, both of them have the same chemical formula C2H6O, but the way the atoms are bonded are different in these two molecules. So those are two different isomers of the same chemical formula. The third type of constitutional isomer can be different locations of a functional group or any substitution. For example, here it is 1 chloropropane and 2 chloropropane, that is, the position of chlorine atom is different in these two different molecules. Stereochemistry was introduced more than 100 years ago. Stereochemistry is the chemistry of molecules in three dimensions. So we try to learn these orientations of atoms around a carbon atom, and that based on those orientations we try to understand different reactions and reaction mechanisms, which will be discussed in the next part of this course. In 1874, Jacobs Van 't Hoff and Charles Labelle independently proposed that the carbon atom will have four bonds in tetrahedral orientations. So for example, if I have a carbon atom at the center and its four bonds, the four bonds will form a tetrahedra, and if this tetrahedra is drawn inside a cube, then it looks like this, whatever is shown here. So this is the central atom, which is the central carbon atom, and the other four are its substituents, which form the corners of a cube. So the consequence of tetrahedral arrangement of bonds of carbon is that for the same molecular formula and for same bonding, if two different spatial arrangements are possible, then those two different orientations or two different arrangements are two different compounds. So for example, I have two molecules here. So I have two molecules here formed by four different groups, and if you look at these two molecules are same because they can be superimposed on one another. But if I do a replacement of one pair of bonds and connect them in a different way, then these two molecules will be different. What we see here, these two molecules are now mirror image of one another. The blue and blue are mirror, red and red is a mirror, purple and purple is a mirror, and the hydrogen is also at a mirror position or mirror image related. So therefore, two atoms, two molecules having same set of groups but arranged in a different way will result into two different compounds. So the way we draw that in two dimension is this. Suppose I have hydrogen here connected to carbon and a bromine atom connected to carbon like this. Then I can have two other groups above the plane of projection, maybe a chlorine atom, and below the plane may be a fluorine atom. So if I draw the mirror image here, this hydrogen is connected to this carbon atom. The carbon atom is then connected to the bromine, which is on the plane of the board, and then I have two groups which are chlorine above the plane of the board and the fluorine which is below the plane of the board. And these two molecules that we have here are mirror image of one another, and they cannot be superimposed on one another. If I try to superimpose, then white goes with white, red goes with red, but the blue and the violet, they don't go on one and the other. So these two are not superimposable and they are mirror image compound. So though these two, although have same chemical formula, are two different compounds. So like that, when you have four different groups connected to a central carbon atom, then we give rise to a center which is called a chiral center. So here in these few molecules which we have shown, if you look at this carefully, at this bond which is shown as with the arrow, this point, we have four atoms, and the way those OH group and hydrogen atom is connected to that are different. So these two compounds are two different compounds. Similarly, here also, at this center, the methyl and hydrogen atoms are connected in different ways. In the first case, the methyl is above the plane of the projection, when the other case, the methyl is below the plane of projection. As a result, it gives rise to two different forms of alanine. The same is seen here, and as well the same is seen here. So this gives rise to different compounds if you have different ways of attaching the group to a central carbon atom. So the stereochemistry of organic molecules can be understood if we understand the meaning of handedness. Why? Because the handedness plays a role in organic chemistry as a consequence of tetrahedral arrangement of the sp3 carbon. sp3 carbon has four atoms connected like that, and these four atoms can be connected to that central atom in two different ways, either this blue atom on the right and this on the left, or the reverse. So with respect to you, it is left and right, and I can have it right or left, keeping hydrogen and this red atom as it is, keeping the hydrogen up and red pointing towards me. So when we try to see this handedness, we try to see the way right-handed people would write and the way the left-handed people would write would be different. For a right-handed people, we write like that, and the left-handed people would write like this. The fundamental reason for this is that our hands are not identical. Rather, they are mirror image of one another. So most drugs and most of the molecules in our body are handed. That means they are mirror image of one another. See, what I am trying to show in this screen is the image of two hands like this, and those two hands are mirror image of one another like this. And when you try to superimpose one on the other, you cannot do that because those two are different in their handedness. So one is right hand and the other one is left hand. Although the fingers try to match, the two thumbs point to different directions. So therefore, these two hands are different, and this difference is manifested in the four bonds of carbon atoms, which are responsible to give rise to different geometries around that central carbon atom. So here in this particular example, you can easily identify that the carboxylic acid group is up in both the cases, NH2 group is down in both the cases, the R group is pointing towards us in both the cases, but the hydrogen here is pointing towards left, and here the hydrogen is pointing towards right. So this means these two molecules are different, and the arrangement of those atoms about the central carbon is different. So this difference in orientation of the bonds make these two molecules completely different. So it will have different physical properties. So when we try to understand the presence of chirality, we try to understand the presence of asymmetry in a molecule, we should also reconsider our understanding of presence of symmetry in a molecule. See, for example, a molecule which is, suppose, water, has a two-fold symmetry or a C2 axis and has sigma planes, mirror planes. Similarly, if I have a metal complex with two groups like this, two groups here, this molecule also has C2 axis and sigma planes. There may be a molecule like this where you have a metal bonded to two chlorines as trans and two ammonia as trans. This molecule also has a different symmetry. What all we have here is a two-fold axis, that is a C2 axis, a sigma plane, and the inversion center I located at the center of the metal ion. Similarly, if we try to draw a carbon based molecule like this, where we have two hydrogens like that and two chlorines like this, which is nothing but dichloromethane, a very well known solvent. This molecule also has a C2 and two numbers of sigma B's. So when any molecule has this kind of symmetry elements, either a two-fold axis or a mirror plane or an inversion center, these molecules are termed as achiral molecules. The molecule containing I is called as centrosymmetric molecule. So, it is the molecular handedness that makes possible many of the specific interactions between molecules that are very crucial in biochemistry. So some of the handed molecules are biologically active and some opposite handedness molecules are biologically inactive or not active as the other one. So for example, plus glucose can be cited here. Only plus glucose is able to help in animal metabolism, whereas minus glucose is unable to participate in animal metabolism process. So when we try to understand the origin of this chirality, we consider three different generalized molecules, CH3X, CH2XY, and CHXYZ. So what we see that CH3X and CH2XY molecules are identical to their mirror image, and hence they are not handed set of molecules. If we make a model of each molecule and its mirror image, we can superimpose one on the other. So for example, if we have this molecule where you have three groups same and where you have two groups same, you take a mirror image of these molecules, you will see that the mirror image can be superimposed on the original molecule without any problem. Therefore, these molecules are not handed or not chiral. But unlike CH3X and CH2XY, if we have a new molecule where all the four groups are different, the molecule is not identical to its mirror image. So we cannot superimpose a model of this CHXYZ molecule on a model of its mirror image for the same reason that we cannot superimpose left hand on right hand. So let us see this by doing a mirror image relationship. So on the left hand side we see a tetrahedral carbon at the center with four groups different, and here we have a mirror. So the mirror generates a mirror image on the right hand side, and that mirror image reflects 1 to 1. But these two compounds are non-superimposable, and as a result, these two are stereoisomers, or these two are two different enantiomers. So this is how you should try to understand here that these two molecules that I have shown you before, these two molecules are mirror image of one another, right? Blue and blue, red and red, purple and with the hydrogen on top. But these two, if I try to superimpose on one another, they cannot be superimposed. Only two atoms, hydrogen and the red atom or the oxygen atom, is superimposed. The other two atoms are not superimposed. So these two are non-superimposable mirror images of the same compound. Rather, they are two different compounds. So we defined enantiomers as enantiomers are related to each other as a right hand is related to left hand. Whenever a tetrahedral carbon is bonded to four different substituents, the situation arises. So a molecule is not chiral if it contains a plane of symmetry, which is very important. A plane of symmetry cuts through the molecule into two parts, and those two parts are mirror image of the other half. As a result, that molecule cannot be a chiral molecule. So here again I am showing in a pictorial manner how these two atom molecules are different. Two asymmetric compounds, two mirror images represent here that the molecules that are related are like this, and this green atom is pointed towards left, whereas the green atom here pointed towards the right. So as a result, these two molecules are different. Now, if we look at this particular case where I have two centers where both the centers have four different groups attached. Here I have hydrogen, chlorine, methyl, and a large group attached to this. Similarly, on this I have hydrogen, chlorine, and methyl, and a large group attached to that. So both the carbon centers are chiral, but overall the molecule has a plane of symmetry. The molecule has a mirror plane, and therefore the molecule is not a chiral molecule. So this type of molecules are called the internally compensated compounds or the meso compounds. You see in these other two examples where I have the carboxylic acids on top and bottom, OH groups on left hand side and the hydrogens on the right hand side, and this dashed line is a mirror plane which actually reflects the top portion of the molecule to the bottom portion of the molecule, and hence this compound is again not a chiral molecule. If you look at this molecule here, what we have done in this molecule is that we have made two changes. First, we have changed the position of chlorine with hydrogen, and then we have made the change between the fluorine and OH and made this molecule. So these two changes made the molecule look like this, and it has again a mirror plane here. So these two changes made the molecule look like that it has an internal plane of symmetry. So therefore this compound is also a meso compound. Here in this particular example, you see that this particular compound has two groups same, and these two groups being same, the compound has a mirror plane, and that presence of mirror plane makes this compound as an achiral molecule. But if I replace the fluorine, one of the fluorines by hydrogen, the mirror plane disappears and hence makes this molecule as a chiral molecule. Let us see in another example that how the orientation or arrangement of molecules make one compound chiral and a different orientation makes it as achiral. As we know that enantiomers are non-superimposable mirror image relations and they are different molecules. Here we have taken the example of cis-1,2-dichlorocyclopentane. Here what we see is that this compound and that compound, they are mirror image, and these two mirror images can be superimposed on one another. Therefore these two compounds are one and the same. But here what we have done is, in case of trans-1,2-dichlorocyclopentane, the mirror image looks like this, and when you try to bring this mirror image and try to superimpose on the original one, this chlorine will form a superimposition with the hydrogen, and that hydrogen will try to superimpose with chlorine, and that does not give you a correct superimposition. Therefore, this compound and its mirror image are two different compounds, and that is why we can consider that this trans-1,2-dichlorocyclopentane is chiral molecule. So we will end this session here, and in the next lecture we will start learning about Fischer projections. Thank you.